I want to take a closer look at some pressure versus volume diagrams. So one of them we have explored is a system where we have, let's say, a pressure sensor and the syringe. And I can create a small volume inside the syringe. We lock this onto the pressure sensor. And the experiment that I can do is now we have atmospheric pressure in here at a volume of 5 milliliters, but then I begin to expand this. I can expand this to 10 milliliters, and the pressure is going to decrease inside and then expand it to 15, expand it to 20, and we can get a measurement with this Vernier software of how that pressure is decreasing. So the graph that we get for that is one where we start with a small volume and a large pressure, atmospheric, and then as you increase that volume, the pressure begins to go down, but it goes down in a non-linear fashion. It goes down in an inverse fashion. Now, this makes sense with the ideal gas law. PV equals nRT. We rearrange this expression, we can see that volume on the other side. This is P versus 1 over the volume, and the meaning of the slope, if you took that inverse graph, would be n times r times t. So that is one look at this pressure-volume relationship. But I want to consider some other possibilities as well. So let's imagine a situation where we start at a small volume, and then the system expands, and it does work on the external environment. Now let's say that the pressure remains constant as this is occurring. So maybe we start at this point, and we go to that point there, and there's a progression in that direction. So that could be akin to this situation, where we're saying we start at a small volume, and work is done on the environment as it expands. So let's say we have this small volume here, and then I let it go, and this expands, and it would do work. So let's say I put a mass on top of here. I could push this down, and it could lift that mass up. So now this environment has done work. This is a positive output, a positive work that is done. Now, in that particular system, the pressure and volume change together. So that isn't an example of this. But this is what we call an isobaric process. So we could have something where the pressure remains constant while the volume is expanding. And the amount of work that gets done is simply the area under this graph. So you take that area equals the pressure times the volume. Let's take a look at those units. You would have the Pascal, or newtons per meter squared, multiplied by the volume, so meter cubed. So this would give you meter cubed over meter squared gives you a meter, so a newton times a meter, which is a joule. So it is a unit of energy, and it says that this is the amount of positive work that the system does to the environment outside of it. Another possibility is what's called isochoric. So we may have a system where you start at some volume and pressure, and then the volume doesn't change, but the pressure goes up. So some sort of system where the pressure is now increasing. This is usually going to be a temperature change at that point. So there's some amount of thermal energy that's put into a system that is able to cause the pressure to rise while the volume remains inside. If you think of a solid, a solid object filled with gas, and then you heat that gas, and the walls are rigid. Although actually that would, so that the volume would not be able to expand, but the pressure within that sealed container would be able to increase. So there is no area under this graph. The area is 0 because it's a vertical line. But there is still energy. There is still an energy exchange happening in terms of heat. So it's not like no work is being done, but no mechanical work is being done. And this is an isochoric process. Now what we could do is we could kind of put this whole system together into a loop. Should have kept my axes here. So maybe we have some sort of process where, let's say we start here, there's some volume and there's some pressure. And now while the pressure remains constant, the volume is going to increase. So there is some way that we can cause this increase in volume without the pressure increasing. And then from that point, so let's say that's step A to B, and there is some amount of work that is then done by the system on the environment in that case. And I'm going to do some other colors. Not yet. Then process B to C might be this isochoric. Maybe there's some way now that the volume now remains constant. We sort of fix that volume, and the pressure is able to increase. So as you go from B to C. And then now the system is going to collapse again. So now you have this large volume that's sort of bursting at the seams with this extra pressure. Maybe some kind of valve opens, and then all of a sudden you can have the fluid. I'm starting to think about what my example is already. Now all of a sudden you're able to have this volume decrease suddenly due to that expanded pressure. So I'm going to, now we come back this way. So originally we went to the right, causing this expansion, but now that this is collapsing, we have to find a way to have it collapse. So we have to have this volume decreases again. So now, sorry, I wanted to double check my notes to make sure I'm talking about the positives and negatives here in the proper way. So I was describing it correctly before, where I say that as your volume is increasing, then the system is doing work on the environment around it, pushing outward on that environment. And then as we go from C back to some point D, now basically this is the environment pushing back on the system and sort of maybe squeezing that volume down to a smaller size again. So now this is going to be considered in this picture a negative work that's done. And it's this entire area here. So all of that. And then maybe we have some finalizing of this process where you go from now point D, let's say back to A again. If we kind of go in a loop here. So from D back to A, now the pressure is going to find a way to decrease while the volume remains the same. Now this is sort of theoretical, but it's getting you to think about mathematically what's going on here. We have this area down here, we have this bigger area. So actually the net work, the net total work that's done throughout this cycle is this area within the rectangle here. So if I want to shade that maybe red. So this is the area that you would get to find out what is the network that has been done by the system or to the system. In this case, it's work that's done to the system. This would be a negative value of work. But honestly, for our purposes, I'm not really interested in whether it's called positive or negative, because that just depends on what perspective you're taking. Are you taking the perspective of the system itself or the environment outside? Well, what is an application of this? Well, it's the pressure volume loop of the heart. All right, so over here we see a similar type of picture of this, the pressure versus the volume, but we're looking specifically at the left ventricle. So if we're coming to our heart, with the right atrium, right ventricle going off to the pulmonary artery, and then we come back in from the pulmonary vein into first the left atrium and then the left ventricle. So this is what we're going to focus in on. What's going on here with the mitral valve and the aortic valve? So our picture begins sort of at the beginning here, the bottom left. So this is the perspective that I was taking in that in the previous picture we were looking at. So right before diastolic filling, we're at both a low volume and a low pressure. So low volume in here because basically it's not filled with blood yet, and also low pressure for that reason. But then as soon as now all of a sudden you're able to get this filling occurring, so the mitral valve opens up, blood comes rushing in, and the volume begins to expand. And as it begins to expand, the pressure remains effectively constant. It does change a little bit, but this picture is showing that this is filling up. This is filling with blood, expanding, expanding. Volume gets bigger. The pressure is remaining more or less the same. And then all of a sudden now, as soon as you get to this point 1, you have this isovolumetric contraction. So now the heart contracts. This valve, this ventricle contracts. It begins to squeeze. So, but the volume doesn't change yet because we haven't popped open the aortic valve. So the squeezing is occurring. The volume is effectively remaining the same though, because there's blood in there. So you can't make the chamber smaller, but it's squeezing, the pressure is going up, up, up. And then at some point now that aortic valve is going to pop open. And as soon as that pops open, now the blood is able to rush out. So that squeeze is constant, sort of consistent. The pressure remains the same, more or less, but the volume decreases as the blood moves back out and it gets to a smaller size again. And then at that point now the aortic valve is going to close, and so the pressure, which was high because that squeezing was occurring, well, now the squeezing sort of backs off. The heart is no longer contracting, the squeezing goes down, the pressure decreases, the volume of this is empty, the blood hasn't filled it back up, so the volume is at a low point, and then we begin again. So diastolic filling, mitral valve opens, this expands in volume, then heart begins to squeeze, pressure goes up. Then the aortic valve opens, blood is ejected, volume goes back down again, and then the relaxation, the heart stops squeezing, and the pressure comes back down again. And if we want to know how much work is done by the heart here, all we have to do is get some numbers. How does that volume change? How does that pressure change? And we can get the area here, and we can make a calculation of how much work has been done. So this is a great example of how we can take some of these pressure volume ideas and then apply it to this human system, the system of the heart.